Hello, everyone. Thank you for joining us today and welcome to Astro 3D ECR Astronomers in Australia seminar series. My name is Anisha Harshan. I'm from the University of New South Wales in Sydney, Australia. And today I'll be chairing along with my co-chair Yifei Jin from the Australian National University. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today. The Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I'm speaking to you from the land of Beregal people, and my co-chair, Yifei, is joining from the land of Ngunnawal country. Both of our speakers are joining from the land of Wurundjeri people of Kulin Nation. We pay our respects to their elders, past and present, and extend our respect to all First Peoples joining here. All right, so why we here? This series is facilitated by Astro 3D, the Australian Research Council Centre of Excellence for All-Sky Astrophysics in 3 dimensions. So COVID has, of course, affected all of our ability to travel and present at international seminars, and that has affected people in astronomers in Australia, especially because of our time zone constraints. So this series was created to provide opportunity to early career researchers in Australia to reach international audience and to try to mitigate that disadvantage. And our next speaker is Adam Batten from Swinburne University of Technology again. Adam is specializing in using hydrodynamical simulations to understand the intergalactic medium.
Yeah. Thank you everyone for coming to attend my talk this evening. So my name is Adam Batten. I'm a PhD student at Swinburne University of Technology in Melbourne. I'm also finishing up this year. So if you're looking out for the job market, think of me. My PhD is looking at the intergalactic medium and trying to understand different ways that we can try to probe the intergalactic medium and understand it a bit further. In particular, I use simulations to do this. And so today I'm going to be talking to you about my recent work at using fast radio bursts and looking at their effectiveness of trying to probe the intergalactic medium and what we can learn about the universe from them. Right. So just so that everyone's on the same page, what do I mean by the intergalactic medium? Well, when I say the intergalactic medium, I mean the low density, high temperature gas that is outside of galaxies. So they're outside the virial radius. So this gas is of density about 1 atom per cubic meter and a temperature of about a million Kelvin. So it's incredibly hot and incredibly low density. So it's a really interesting phase of the universe to be studying. But you might be thinking, well, why do we care about the intergalactic medium? It doesn't have anything, it doesn't sound like it's got really anything in there. So why is it important? And I want to give you 2 main reasons why we should care about the intergalactic medium. The first is that the intergalactic medium actually contains most of the baryon matter in the universe. And so when we think about doing a cosmic census, where basically adding up where everything is in the universe and trying to divide up in what all the different parts are, it turns out less than 20% of all the matter in the universe exists in what we would typically think of as structures. So galaxies, if you add up all the light from every galaxy that you see, it adds up to only about 7%. Same thing with the circumgalactic medium, so like the local neighborhood around galaxies is only about 5%. And then clusters are the next big component of 4%. So the total is only about 18%. However, that means the rest of the universe, the other 82%, is in the intergalactic medium. So when you try to understand the universe and how matter has evolved over time and what the bulk material is in the universe is doing, you need to understand the intergalactic medium because that's where most of the matter is. The second reason why you should care about the intergalactic medium is that galaxies and the intergalactic medium, they evolve together. And what I mean by this is that processes inside galaxies like star formation, black holes, feedback, AGN, supernovae, that sort of thing, they can drive winds into the galaxies. And these winds can basically blow out gas and dust from the galaxy into the intergalactic medium, basically escapes the galaxy. And this gas and dust then enriches the intergalactic medium and kind of pollutes it with new elements and kind of heats it up a bit as well, changing how the intergalactic medium interacts with the galaxy itself. And similarly, material that's inside of the intergalactic medium can flow into galaxies. They can be accreted onto it, and this pristine kind of less enriched material can then be the new gas that forms stars inside the galaxies. So there's this cycle of inflows and outflows of galaxies and the intergalactic medium. And so the evolution of galaxies and the IGM is linked very deeply. And so you can't fully understand one without understanding the other. So hopefully these couple of reasons can convince you that the intergalactic medium is super important to study. However, I want to talk to you about a couple of problems. So first thing, like I was telling earlier, the density is really, really low. So it's 1 particle per cubic meter. And it's also incredibly hot. The temperature is about 1,000,000 Kelvin. This leads to the unfortunate lack of favorable optical and ultraviolet transition lines, meaning that it's really, really difficult to observe the intergalactic medium in optical and UV. And this is because the density is really low, which means that emission and absorption lines are particularly difficult to come across. And because it's so hot, the emission and absorption lines you do come across are typically in the X-ray. This is because all the gas is so hot that it's ionized. And so most of the electrons are removed. And so only these high ionization species are left. And so it's extremely difficult to observe the intergalactic medium, particularly from the ground, but also from space as well, which has led to the historic missing baryon problem, where at low redshift near to us, so in the nearby universe, about 30% of all the baryons in the universe were missing. This is not because we didn't know where they were. They're probably in the intergalactic medium. We just couldn't find them because we didn't have any transition lines to observe them easily. And so this was the problem. And so how do this FRBs come into this? And so first, we're going to talk quickly a bit about FRBs again. And so what was an FRB? We don't really know. No one knows what an FRB is. It's likely that they are somewhat associated with magnetars, but we don't know for sure. The important thing for an FRB, in my case, if we want to understand the universe, is that they're incredibly sensitive to electrons. And so an FRB, as it transverses all the way to a telescope on Earth, it interacts with a bunch of electrons along the line of sight. And this gives rise to a property of the FRB called a dispersion measure. And so this dispersion measure, if we look here on the plot, this is a plot here of frequency of the FRB as a function of time. And so this is the arrival time of the burst. And so you can see that the high frequency signals, so this kind of yellow bit at the top, arrive before the low frequency signals, which means that the high frequency light arriving sooner than the low frequency light. This means that the burst has been dispersed in time. And so you can actually measure how much this is dispersed, and it's just a function of electrons, column density, and frequency. So if you can measure the frequency and arrival time of the FRB, you can directly measure this quantity called dispersion measure. So this DM here is not dark matter, it's dispersion measure. And this is essentially just electron column density. How many electrons did this FRB go through from its source to our telescope? And this is the key quantity that's going to help us probe the intergalactic medium. Because like I was saying, the intergalactic medium is ionized, so it's mostly electrons. And so there's a couple of breakdown of what the dispersion measure is inside into different components. There's a couple ones. So for instance, how much electrons are there from the Milky Way when the FRB goes through it? How much gets from the intergalactic medium, and also how much from the host environment. For this talk here, I'm mostly going to focus on this middle yellow one, the DM cosmic, so the cosmic component of the dispersion measure. This is just the sum of the intergalactic medium, so how many electrons you get from the intergalactic medium, and any sort of galaxies that are in the path along the way. So if an FRB just happens to go through the CGM or a galaxy in the line of path, it gets added to the cosmic component. And so the key point about the dispersion measure is if we take a model of the universe and we just assume that it's completely ionized hydrogen, what does the dispersion measure look as a function of redshift? So this is the cosmic dispersion measure as a function of redshift. What is the estimated amount of dispersion you should get from an FRB going off at a given redshift? And this is this line here of a universe entirely ionized hydrogen. But however, if you kind of make your models more complicated, add hydrogen, helium, add your different levels of ionization stage, you maybe add galaxies, you kind of get a different slope of this line, which means that the slope of this line is very much dependent on how many electrons you have in the intergalactic medium. The less electrons you have in the intergalactic medium, the shallower the slope is. And you can also do models from simulations to kind of estimate these lines as well. And what basically I want you to take away from this is that the slope of this line tells you how many electrons there are. And so you can model, based on the models, you can work out what the slope of the line should be, and you should be able to compare to observations. And additionally, the scatter around this relation, this is very much dependent on how lumpy the universe is. So if the universe is very homogeneous, the scatter around this relation is very narrow, or almost none. If it's the universe is very, very lumpy, and it's very much high voids and very much clusters, then you get a very big scatter around these relations. And this is what was used historically in 2020, where McCourt was able to recover the missing baryon problem. Using 5 FRBs, they're able to show that all the baryons are actually in the intergalactic medium, and FRBs can find them. So excellent. It's been shown that FRBs can probe the intergalactic medium. What else can they do? So this is what my work has been doing on. And so this is one of my papers that have just been accepted in M&RAS. You can look at this up here, but I'm going to talk to you about some of this work today. And so what do I use? I use the EAGLE simulations. These are a suite of hydrodynamic simulations that try to replicate galaxy properties on a large scale. And so they have hydrodynamics and they've got n-body, and they cover a huge volume, and they evolve the universe all the way down to redshift 0 today. And they have lots of abundances and ionization background and galactic winds to correctly evolve galaxies. And so they've got excellent resolution and particle masses, which gives us fine grain resolution of what the universe looks like. And so if I want to look at what FRBs look like through the simulation, I want to send basically lines of sight through our simulation. So basically send a pinpoint through the simulation and work out what is the total dispersion measure along that line of sight. And to do that, what I do is that I divide the box up into a grid, 32,000 by 32,000, and then I send a single line of sight through each center of each box. And this gives us over 1 billion lines of sight. And after we've sent a line of sight through that, we calculate what the ionization level is, the hydrogen and helium, and we add them together basically to get the number of electrons there are. Because we're going to assume that almost the entire universe is just hydrogen and helium. And then after we've got the number of electrons along the given line of sight, we now have dispersion measure. So we can basically have a map of what dispersion measure looks like through the simulation of EAGLE. And this is some examples of what they look like. So in the top here, I have what the dispersion measure looks for a local observer at redshift 0, 1, and 3. So you can kind of see these little lumpy bits. These are from like galaxies. And as you get like in a smaller universe, you see that the dispersion measure is much higher because the universe is smaller. And in the bottom panel here, I have what the dispersion measure contribution is to the redshift 0 observer. So at redshift, an FRB going at redshift 3, how much does this contribute to the redshift 0 detection? And so these maps basically tell us what the dispersion measure is throughout EAGLE. And once we have these maps, what we want to do is then we basically line them up all next to each other, and we send lines of sight through all the maps all the way up to redshift 3, such that we can have basically a big distribution of what the dispersion measure looks like in EAGLE. And this is what we have here in a plot here. I'm going to focus on mostly on the left. So this is one of my main results from my paper. Is that on the left here, we have redshift on the x-axis, and on the y-axis, I have dispersion measure. And so the black thick line is our mean dispersion measure value at any given redshift. So what is the expected dispersion measure from an FRB at a given redshift? And the dashed dotted lines are the 1 sigma, 2 sigma, 3 sigma confidence intervals. So you can kind of see that there's these large, big PDF tails. These are probably from FRBs that go through some sort of overdensity, like an intergalactic medium filament or a galaxy cluster. And so any ones that intersect one of those end up in this top part of the PDF. And similarly, any sort of FRBs that don't go through anything and mostly go through voids end up in the low region of this PDF down here. And if we compare our model that we just got from EAGLE to work of everyone else, we can see that ours goes basically straight through the middle of everyone. And we have also done resolution tests and everything on our simulations to check if this mean is dependent on a resolution. We find no difference. So we know our mean is robust against all resolution effects and box sizes. So excellent. So one of the other main results of my papers that I want you to take away from this is if we go back to this mean and the PDFs and we compare these to localized FRBs. So here again on the plot, I have redshift on the x-axis and on y-axis dispersion measure, and you got the 1 sigma, 2 sigma, 3 sigma confidence intervals with our mean running through it. I've plotted here all of the localized FRBs as of November 2020. And so what I mean by localized is that these are FRBs that have a known redshift because they have a known galaxy associated with them. I've also color coded them based on whether they are repeating or non-repeating FRB. And you can see that from redshift 0.3 to 0.7, our model is pretty good. It matches the observations quite nicely. However, in this low air region down here, less than 0.3, we find that most of the FRBs appear in the 2 to 3 sigma above the mean region. So there might be a couple of reasons why this is the case. One, we could be just in this redshift regime, we are more sensitive to the really high DM FRBs. And so we're not detecting ones that are closer to the mean. Two, these FRBs could all be going through intergalactic medium filaments. So or maybe galaxy halos that we haven't seen that just boost the DM. And so what is the cause of this? Number three, I forgot, is these could also have higher halo counterparts. So whatever the source environment around these FRBs, they could have some higher contribution to the overall DM that we're not accounting for. And so that would also cause these DMs to be higher. So which of these three different reasons could they be? I am predicting that they could be going through intergalactic medium filaments, and then that's why they're going through, have much higher DMs than all the others. And why do I say this is the case? As well, this FRB here, 190608, it's actually had some other analysis done on it. So if you take this FRB in 2020, Simhar and et al, they did a IGM reconstruction on what the IGM should look like in front of this FRB. So what they did is they took the galaxies from SDSS, the Sloan Digital Sky Survey, and then they worked out where the IGM filaments should be in front of this FRB. And they kind of then converted that into density. So that's what we're seeing here on the left here, is that distance from the FRB is a function of density. And you can see these peaks, these correspond to over density along the line of sight.
Adam, that's 5 minute mark, sorry.
Awesome, good. And so this density, if you then convert this density into dispersion measure, which is what you see in blue, you basically work out what is the dispersion measure that would come from the intergalactic medium filaments that are in front of this FRB. And you can see this basically double compared to this red line, which is the average mean one. So this FRB definitely goes through an IGM filament. And so the question is, do all the other ones do? If this 190608 definitely does, do the others? And so that's what I'm working on. I'm part of this survey. Yeah, so do these others go through filaments? The answer is maybe. We'll find out because I'm part of this survey where we're using the AAT to try and map the foregrounds of these galaxies as well. So what we were trying to do is then work out where the intergalactic medium should be in front of these FRBs, and then work out do they go through intergalactic medium filaments, or are they just have really high halo contributions? And so this is working coming up. So hopefully keep tuned into this survey. The other final thing I want to talk to you about today is, well, FRBs have been shown to be able to effectively find missing baryons. What else can they do? My question was, can we use these as probes of galaxy feedback? Right, so remember back to galaxies, they have outflows and inflows. So material that was inside of galaxies can be kicked out of galaxies, and material that can fall into galaxies also takes material out of the intergalactic medium. So there's kind of regulation between what is the feedback of a galaxy and towards what is feedback of the galaxy and how does it interact with the intergalactic medium? Well, if there's higher feedback, you might think, well, maybe there's more material in the intergalactic medium and there's less in galaxies, so they'll change the slope of the relation or change the scatter around it. And so that was my question that I wanted to work out. And so what I've done is took Eagle and I did two different other simulations, one that has no AGN and the one that has more efficient AGN feedback. And so we wanted to see what is the difference in the dispersion measure relations and the scatter around it compared to these different types of simulations. So basically have very, very different AGN feedback. And then this is the results from my paper that's coming up in hope in the next few months, is that we focus on one on the left first, this is the redshift dispersion measure relation. We find that the DMZ relation is incredibly robust to actually changes in galaxy feedback. And so the different feedback models produced almost the exact same DMZ relation. So the DMZ relation is not really a good way to measure galaxy feedback properties. However, what we did is then instead of looking at the mean, is if we look at the scatter around the mean, so the variance, we find there is actually a big difference between the models. And in fact, the weaker the AGN feedback or no AGN feedback, the larger the scatter is between around the DMZ relation. And the stronger the feedback is, the lower the scatter. And so question you want to know is like, how could you measure this with FRBs? Can you like get enough FRBs to work out what the galaxy feedback strength is of a particular population of galaxies? And so you want to know how many FRBs in what range. And so I picked maybe the range between 0.5 and 1. This seems to be the appropriate level of range where you have enough difference between the models and it's feasible to detect them. And so this is kind of this range in here, and look at the scatter. I sampled these FRBs to work out how many you need. And the core takeaway of this is that the more similar the models is, obviously the more FRBs you need. And to differentiate between the reference simulation that is of standard feedback and the strong feedback simulation, which increases the temperature dumped into the gas, you need about 9,000 to 10,000 localized FRBs, which if you were to find a localized FRB every single day would take you 25 years. So it's difficult is the question. Using FRBs to measure galaxy feedback is difficult, and you're going to need a lot more FRBs than what we are finding at the moment. And so I'm just going to summarize what I've just said here in my slides. So FRBs are providing a new way to probe the electron baryon distribution in the intergalactic medium. My paper that's just been accepted in MN-RAS, I use the Eagle simulations to calculate DMZ relation and the scatter around it. We find that most FRBs are in the 2 to 3 sigma regime, and they kind of possibly intersect with IGM filaments. And my other paper in prep is where we're looking at galaxy feedback and the dispersion of FRBs. We find that the mean DMZ relation is very robust against galaxy feedback. However, you might be able to use the scatter to be able to measure galaxy feedback. However, you're going to need about 9,000 FRBs in the range of 0.5 to 1, which is a lot. And you're also then going to need to do a large number of large box simulations to measure the differences between these different feedback prescriptions. So thank you.
Thank you, Adam. It's a great talk. We can now move on for some questions if there are any from the audience. Yifei?
So good. So we have some questions from the chat. So basically, they're from Jelai. Jelai, do you want to ask the question on your own?
Okay, sounds good. Maybe Hamza can go first because Adam, we go to the same uni, so I can ask him later too.
Okay,
I
we
think
have.
that's fine. I mean, feel free to. Are you sure?
Yeah, you go first. You go first.
Okay, great. Thanks a lot for a great talk. I had a quick question, which maybe you said something about, but if so, probably I didn't catch it. If I recall correctly, you're using an integrated measure, right? I was wondering how you get the detailed density profile. You showed a plot where you. Yeah.
Oh, so okay, we go back. So you wanted to know.
Yeah. So the integral.
Like wait, is this plot? This plot is me or? So what they did. So this wasn't my work. This was someone else's work. What they did here basically is they took the SDSS galaxies. They basically took all the positions, and then took all of the galaxies that are closer than the FRB, and then basically use this kind of fancy like neural network MCMC kind of thing to map out where the intergalactic medium filaments should be connecting the galaxies, because the galaxies basically should follow the filaments of the intergalactic medium. And so by basically connecting the dots literally where all the galaxies are, they're able to kind of make a map of where all the cosmic web should be. And then from that, they were able to convert that into density, basically, because the more galaxies that are in a particular bit, the denser the gas should be. And so that's how they kind of did these like density peaks and then converted that into electrons.
Yeah, that's very interesting. Okay, so if they used a technique like this, I'm expecting that there could be some scatter around this if you do different realizations.
Yes, yeah. So depending on what model you do, you get different values. So this is kind of like some examples of this is the survey that I'm a part of called Flynn where they did the same data set basically, and then different realizations of the equivalent universe that would make this the same distribution, if that makes sense. So you could have the exact same distribution of galaxies, but different IGN filaments. And so you take some ensemble average basically of them. You can kind of see like all the different scatter that you could get.
I see. Thank you so much. Very interesting.
Yeah.
We have another question from Luca. Luca, would you like to ask a question?
Thanks, Adam. That's really interesting. I have actually two quick questions. The first one, you mentioned IgM and then you went after the effect of IgM feedback. I'm curious, does Eagle also include the proper characterization of the CGM?
So does it have a good characteristic of the CGM? Depends. It's not really resolved enough to measure the CGM itself.
Yeah.
But so what we're doing is looking at what is the distribution of just lines of sight through all of Eagle.
Right.
So if I wanted to, I couldn't go take a galaxy and then do a line of sight through the CGM because that might not be resolved. But if I take an average property of the entire population, basically this was a first proof of concept. Could you do this, and how many FRBs would you need? You'd need a lot, and you need much better simulations. Is the answer?
Yeah, makes sense. And I guess the other curiosity was interesting, the spread for different AGL feedback. Have you considered doing this with something like Illustris or other simulations? Because I would expect that the scatter might be larger due to implementation of different physics.
Yes, that is something I have definitely considered and wanted to do. The limitation is time in my PhD. Yeah, basically I've spoken to other people that have done similar similar line of sight through Illustris and talked about maybe converting some of their code and everything at some point. Basically the limitation is time and stuff to be able to do that, but it is something I really want to do at some point. Yeah, is to compare definitely heaps of different feedback types.
Yeah, looks cool. Thank you.
We can take Gilai's quick question, I guess.
Okay, cool. Actually, my second question is related to what Luca asked. Do you expect the results your main results to be similar if you were to use other simulations, Adam?
So it's similar in some cases and different in others. So Eagle and Illustris or Illustris TNG, they have different implementations of galaxy feedback, and so Eagle does this heating mechanism where it heats the gas around it, whereas Illustris is a slightly different mechanism. I can't remember off the top of my head. It's a bit more energy driven, and or I think it's momentum driven actually, and Eagle's energy driven. And so the different types of feedback could lead to different shapes of it. I just don't know because I haven't done it, but I'm imagining that it could. But that's something that I need to do.
Yeah, thanks.
And thank you so much for attending. And the next seminar will be at this time next week on 3rd June when Simon Murphy and Aditya Manuel will be talking to us. We hope to see you then. Thank you so much for attending. Bye.
Thank you. And thank you for organizing.